Hi everybody. This is the part 3 in our webinar series on porosity. This webinar series has been focusing on controlling porosity, basically providing an overview of what we know about porosity in die casting, basically the details of how the physics of porosity formation works. The last webinar, which I guess was about a month ago now, we talked about the effect of process parameters, what level of control we actually have on the shop floor regarding porosity, and what we saw was that we don't really have as much porosity, as much control about porosity as we think we might have, and certainly not as much control as we would like to have with respect to these processing parameters. So today, in part 3, we're going to talk about porosity control through the design of the casting itself and then the design of the tool. Okay, so the outline of what we're going to be talking about today, we're going to provide some background. As I said, it's been a month since we did the last couple of webinars, and so just review a little bit of the material. Then we'll talk about the effect of casting design and then the effect of tooling design on porosity formation in die castings. And then we'll save the questions till the end. I mean, certainly we could probably take a month or more and talk about casting design and tooling design. Obviously, we don't have that much time, so the goal today is just to take more of a shotgun approach, throw out a lot of ideas, and if you want additional information on the various concepts, you can dig out the papers from the NADCA Technical Archives. That's free for NADCA members. And then you can, in your own time, kind of find out more information about the concepts we're going to discuss today. And certainly I would highly recommend the Technical Archives. I use it a lot to dig out technical information. You can search based on the year, you can search based on the author or a subject, and certainly it's an easy way to find out a lot more information about some of the concepts. So let's talk about this slide again. We've talked about this in the last 2 webinars, so I'll just talk about it quickly here. But this are the results. This pie chart here on the bottom right are the results of the survey that NADCA did of end users. Was asking basically end users what are the biggest problems they have with die castings, and you can see 35% of the respondents said porosity, and then another 32% said other defects, many of which have the same origins as porosity. So basically, if you add these two together, you've got 32% and 35%, basically 67% or 2/3. So basically 2/3 of all the problems that that end users have are related to porosity or porosity-related defects. So based on the information we've already presenting, if you've been following the webinar series, it should already be clear that the design and shape of the casting is going to have a big impact on porosity. And much of the information we've been talking about has already been heading in that direction. For example, if you've been having a problem reducing porosity on the shop floor, if you run into a wall in terms of minimizing porosity, maybe you've already come to the conclusion that it's the part design, not the casting process itself, that's causing the porosity. So we need to note that it's not just casting design, but also tool design that can cause problems. So obviously it's important to address both of them, both tool design and casting design. Certainly it's much easier and much cheaper to get the part design and the tool design correct up front, rather than doing a series of experiments on the shop floor to try and get a bad die design to produce acceptable castings. Also, it's not easy and also not cheap to change the die design once the die has been built. So it's much better to try and get everything correct up front to avoid having to make any significant changes to the die. Again, we've talked about this slide in the previous webinars, but we need to keep in mind where the porosity is coming from. As we talked about before, there's 2 major sources of porosity: solidification shrinkage from the volumetric shrinkage as the metal solidifies, around 6% in aluminum alloys, a little bit less in zinc and magnesium. And then the second source is gas entrapment, gases from different sources. And often it's difficult to tell which is which. When we measure the amount of porosity in actual die castings, it's generally much less than the 6% volumetric shrinkage that we just talked about. So certainly we can account for all the porosity based on shrinkage alone. Now, I'm not saying that all the porosity is coming from shrinkage, but when we think about it, what we need to do is hold shrinkage and gas on an equal footing. And if we do this, it'll help us to troubleshoot problems better when we're looking at issues related to porosity. So in the last webinar, we talked about process parameters, such as some of the things shown here. And what we saw is that we do have some level of control over the formation and the location of the porosity, but ultimately it's going to be the part design and the tool design that's going to have the ultimate control over the formation of porosity. Certainly you can take a good die and make bad castings, but it's much more difficult to take a bad die and make good castings. So you really want to make sure up front that you get the casting design correct and get the tooling design correct. You want to get those correct up front before you start cutting steel to make the die. So let's start talking a little bit about casting design and tool design. Within casting design, obviously the largest control we have is in terms of the shape of the casting, and obviously that's going to have a big influence on where the porosity is going to end up. Of course, we have to design to the alloy. We often pick an alloy to provide predetermined mechanical properties, so the alloy choice should also factor into our porosity concerns, and we've talked a little bit about that in some of the previous webinars. Regarding tool design, we need to optimize for the machine we're going to run it on. We need to make sure the gate's in the right location, make sure the runners are correct, the vents are in the right location, consider the placement of the cooling lines to control the thermal profiles in the die. And we're going to talk about some of these things later on as we go through the webinar. And then in some cases, we might want to use squeeze pins, and these can be used to minimize porosity at a specific location in the castings, and we'll just touch on that a little bit right at the end of the webinar. So let's initially talk about casting design. So the first thing we want to do is to pick the die casting process that we're going to use. Historically, there's only really been one, high pressure die casting. But these days, there's some modified die casting processes that can give you higher integrity castings, and some of these are high vacuum die casting, squeeze casting, and semi-solid casting. So, for instance, if we look at these castings on the right-hand side here, the top one is a drivetrain component, and the bottom one is an inner door panel for a small SUV. They both have different requirements, but they both require very low levels of porosity. So if we look at the top one first, this is a casting for a drivetrain. It needs essentially zero porosity and also can't leak. So this thicker wall type of casting is being produced by squeeze casting. With squeeze casting, we use very large gates. We use very slow die filling speeds, generally vertically orientated shot sleeve. The die filling speed is of the order of seconds rather than milliseconds. And then we use a very high intensification pressure to get rid of the porosity. So the slow filling minimizes gas entrapment. High intensification pressure through large gates helps get rid of shrinkage porosity. So basically up front, if we're going to be using the squeeze casting process, we need to be designing for the squeeze casting process. Now, we don't have the option of squeeze casting for the larger castings. The large casting, this inner door panel, the bottom casting, it's about 4 feet by 4 feet, It's got pretty thin walls, so we can't use squeeze. The low filling speed with squeeze, we're just not going to fill the casting. It's going to freeze off before we are completely filled. So instead, with that process, this part's being produced by high vacuum die casting. So if we're producing this kind of component, we need to be designing up front for the high vacuum process. It's large, it's got long flow distances, thin walls, needs low porosity, so it's ideal for high vacuum. Here's a couple more type of castings. The upper right is a decorative casting. It's got the surface coating to provide the color. No real porosity concerns here. Don't need to look at a high integrity die casting process, but we do need to make sure that the porosity is not totally out of control. But we do obviously need to provide a good surface finish, so conventional high pressure die casting is ideal for this type of process, for this type of part. The bottom casting is a shock tower for a BMW car produced in this country. This casting is structural, safety critical, so that during a crash, and when the car's in a crash, the casting's got to fail in a ductile manner. It's got to bend and absorb energy during the crash. If it just shatters, then it's not going to absorb any energy, and that's detrimental to the passengers in the car. So the casting has got to be very ductile. If we have porosity, that's going to reduce the ductility. It's also thin walls. We need the low porosity we just talked about. So another example of high vacuum die casting. Here's another common example. This is the pump handle for a gasoline pump at the when you go to the gas station. Obviously, this is a leak critical casting, so you need to kind of think up front. Should I impregnate this casting? Is this the type of casting I'm going to need to impregnate, or should I just avoid machining away the dense skin on the casting? Certainly many of these gas station pumps are impregnated. We're not really concerned with the mechanical properties here, just really concerned about preventing the gasoline from leaking out of the pump. So we impregnate this casting, we fill the voids, prevent the leaking, and in this case the gas doesn't dissolve the impregnation material. So, so another thing, all these different die casting processes, we're also going to get different mechanical properties. But basically the point of showing all these castings is that we need to design the die for the appropriate process. With conventional die casting, we obviously use conventional gating. With high vacuum die casting, we use a different type of gating, generally use a much higher number of gates. With squeeze casting, you normally use a single gate, but much thicker gate than you would do with die casting. And so the point is that it's very difficult to change in mid-stride. If you design the die for conventional die casting, it's very difficult to change it to high vacuum die casting or squeeze casting. So you really need to think up front, you know, which process am I going to use it for? So yeah, very difficult to change in midstream if you're not producing the required quality with whatever process you initially chose. So again, talking about choosing the process, generally when you have a casting with uniform thin walls, we're looking at the conventional high pressure die casting. We're trying to take advantage of the skin effect, and we'll talk about this later on in the webinar. But generally we're going to get fine dispersed porosity. For castings with thicker sections, maybe you want to look at squeeze casting or semi-solid casting. This is ideal for these thick section type of castings. You need very large gates to help feed the solidification porosity. The casting shown on the lower right here is a turbocharger impeller. The one on the right is penetrant tested on the section surface, and basically showing zero porosity. And that was achieved by using a very large gate, about a 2-inch diameter gate on that part. So what does all this mean? So basically up front, while designing the casting if possible, and certainly when designing the die, you need to pick the die casting process you're going to use. And also you need to think about what secondary operations you're going to use or pick, such as impregnation. So if my goal is to minimize porosity, but willing to impregnate if it leaks, if I find I can't get the porosity level I need, you could end up making a casting that's difficult to impregnate. So if I think I might need to impregnate, you should design the casting for the impregnation process. This is basically going to save you a lot of heartache and probably some considerable cost too in terms of die changes and maybe some other issues. If you're concerned about pores in a heavy section casting, you should consider a high integrity casting process, squeeze casting or semi-solid casting, which helps to control the porosity in the casting. So don't just say, you know, this is going to be a very difficult die casting and then live with tool changes or live with high scrap rates or any other things that are going to add significant costs. We now have all these different tools, all these different processes available to us. So basically use these to your advantage when you're thinking about how to make the castings. Okay, so the next question we're going to talk about is that of porosity tolerance. We talked in previous webinars about the porosity characteristics of the process, so that basically porosity is essentially present in all die castings. We can control it and in some cases eliminate it. Start out by saying we could get as much as 6% porosity based on the volumetric shrinkage, so I'm doing very well if I'm below that level. So if we look at mechanical properties, and that's what the slide is showing here, on the top we're showing the ultimate strength, and we've got elongation here in the middle, and then yield strength on the bottom. And this is shown as a function of the density of the castings. So basically we're showing three types of castings. The A0 castings have got zero porosity, no porosity, basically 100% sound. And so this is obviously the best I'm going to do for this alloy. And then the A2 castings have got 5% porosity. So most of the die castings that we're going to be producing are going to be somewhere between the A0 and the A2 castings. So in terms of porosity content, when we increase the porosity level, we do see a drop in the ultimate strength. Very little change in yield strength. The biggest change is in ductility. So if I'm making a casting where mechanical properties are critical, I might be very interested in controlling the porosity level. Then if I look at creep, this is what we're showing here. This is the minimum creep rate against density. And so obviously as density increases, then porosity is decreasing. I see a similar kind of trend here. But with small levels of porosity, I don't really see a big impact on creep rate. So we can here look at a little bit more data in terms of porosity tolerances. With yield strength, the loss in strength with porosity is basically related to the reduction in the load area. So for example, if I have 5% porosity, I've got 5% less area of the casting over which to distribute the load. So basically you've got 5% higher stress on the remaining cross-section. And so unless we get huge amounts of porosity in the casting, generally we don't see much of a strong correlation between yield strength and porosity content, and that's basically what we're showing here in the upper graph. We do see a better correlation when you plot yield strength against dendrite arm spacing, and that's what's shown here. And dendrite arm spacing is basically a function of the cooling rate. And so what does that tell me? Basically, for the example of yield strength, it's not porosity that's changed in yield strength. We saw earlier that elongation does drop off with increase in porosity. We can also see that porosity reduces impact energy. However, impact energy is often low for die castings, not just because of the porosity, but because of the high iron concentration of the alloy. And so that's less important again. Fatigue life, however, fatigue is very dependent upon porosity. Fatigue life is going to be controlled by the size of the largest pore. So if you start to get large pores in the casting, you're going to see a significant fall off in fatigue life. So let's talk a little bit about impregnation while we talk about properties. We introduced impregnation a few slides ago, and basically, when should I consider impregnation? Well, obviously, you should consider impregnation when the leaking causes an unacceptable condition in the castings. So the type of casting shown here, valve bodies, valve covers. These are castings where all I'm concerned about is whether or not they leak. Don't really care too much about mechanical properties. They're not really a structural casting. And so this is when I might think about impregnation, or at least enter the discussion up front when I'm starting to design the casting and the die. Generally, the impregnation material doesn't impact mechanical properties, so it can't help with a structural casting. You're not going to, by reducing the porosity by impregnation, you're not going to have an impact on mechanical properties, but obviously you are going to impact is leaking. And so you can think about impregnation when you've got a casting where leaking is an issue. So what does this mean? So some properties are very dependent upon the porosity level. Certainly the elongation, ductility, fatigue. Certainly we cannot tolerate a lot of porosity if these properties are important to us. But often porosity is not that important. We need to design to accommodate the porosity, but maybe we don't need to go to great lengths to eliminate it just because we don't like it. Don't spend a lot of money on trying to totally get rid of it if it's not a problem. If we are concerned about porosity, maybe we should consider impregnation. Impregnation materials are available that will certainly outlive all the conditions that the casting is likely to see in service. And then finally, in general, the size of porosity is probably more important than the amount of porosity, so especially when we're considering fatigue and ductility applications. So now let's talk a little bit more about the shape of the casting. Certainly, and we've seen this in some of the previous webinars, the shape of the casting is going to impact porosity formation. If you want to make a pore-free casting, the easiest shape is going to be to cast a wedge, where we have the thick end of the wedge closest to the gate and the thin end of the wedge away from the gate. We use a runner and a gate thicker than the wedge, and this is going to provide directional solidification. The thin end of the wedge that's furthest away from the gate is going to solidify first, and then basically the solidification front is going to move back to the gate. And this is therefore going to provide optimal feed in the shrinkage. And certainly in this kind of case, we can get a casting with no porosity. Obviously, in the real world, we're not casting wedges. We need to produce more complex shaped castings. So let's introduce some rules of thumb in terms of helping to control porosity. So number one, uniform wall thicknesses. Certainly this encourages uniform flow as we're filling the die, and therefore we're going to get less air entrapment. And it also helps with directional solidification to help feed the entire casting, again with the objective that the gate solidifies last. Secondly, we need to design for gating. The casting is going to contain complex geometries most likely. Maybe you're going to need slides and cores and things like that in terms of making the shape. So when you're designing the shape of the casting, it's ideal if you can be thinking ahead about the location of the gate. If it's very complex and there's lots of slides and it's difficult to come up with where the gate's going to be because of the complex orientation, maybe it's better to eliminate one of the cores in the slide, maybe machine a hole rather than core it to allow a better gate design. That's going to help produce a better quality casting. So in the long run, maybe you're going to get lower porosity, lower scrap, and lower costs. So machining the hole might make it more expensive up front, but by running a lower scrap rate, then your overall cost can potentially be lower. So something to think about. Let's talk a little bit about wall thickness, and I think we talked about this a little bit in some of the previous webinars too. In general, the strongest casting is going to be the thinnest casting, and this is a result of the dense layer on the surface of die castings, and what we're showing that here, and you can see the dense layer here on the thin casting, and a dense layer here on the thicker casting. So what happens is, as the liquid metal enters the die, the hot liquid contacts the cooler die surface, and you're going to get very rapid solidification of a surface layer. And so you don't get too many opportunities for defects to form in this initial surface layer. So you get this very dense surface skin, and as it's dense, you tend to get very good properties in this area. As you move towards the center of the casting, you tend to get more porosity. You can see this here in the thicker casting, where you get this porous, more porous region in the center, and then also in the thinner casting. So generally, the properties in the center, in this more porous region, the properties are not as good as they are in the dense surface layer. So how important is this surface skin? So this is a data from a NADCA paper. The paper is identified down here. This is for magnesium alloy AZ91D, but certainly we can find similar data for aluminum and for zinc also. So if we focus on the bottom chart here, what we're looking at is mechanical properties, yield strength, tensile strength, and elongation for 3 different thicknesses of a casting. So we've got a casting produced at 1 millimeter thick, 2 millimeters thick, and 6 millimeters thick. And you can see that the thinnest sample, the thinnest casting, has got the highest strength. And so if we look here at the yield strength, 186 for the 1 millimeter down to 125 megapascals for the thickest casting, and the same trend for ultimate strength. If I get my cursor to work here, this shows the ultimate strength as cast at 245 going down to 183. But then the researchers, what they did is they removed the skin from all the 3 castings. They removed about a 125 micron layer from both sides, and that's this data here. So now we're looking at the yield strength with the skin removed, and now we're seeing basically no difference between the castings. And then the UTS with the skin removed, again, pretty much no difference between the castings. So what it shows is that the skin is providing much of the strength. And if we look at the thinner casting, to go back to the previous slide, you can see that the dense layer for the thinner casting is a much bigger percentage of the total thickness. So the thinner casting has got overall higher strength due to this surface dense layer. The dense layer is a much smaller fraction of the overall casting for the thick casting, and that's why it has lower strength. So if we can look at flow porosity, some shapes just don't fill very well. For example, the square plates we're looking at here in the top left, they tend not to fill very well, and so we tend to get lots of gas entrapment. So we want to try and make sure that we create geometries that we can easily fill, and certainly there's lots of data in the NADCA publications on how to fill various shapes. Then maybe we need to modify the design for optimum castability, and this is shown here with these 2 castings shown in the bottom left. The left-hand casting, it shows how a part should be designed when it's being produced by machining. We want to try and remove the minimum amount of material. We've got sharp corners and things like that. However, if I want to produce that by die casting, that left-hand casting is not a very good design for die casting. What we want to do is modify the shape to make it easier to fill without introducing defects, and that's what's shown on the right-hand side. This is the same part, but redesigned for die casting. What we've done is we've reduced the wall thickness, we've provided nice radii to promote better filling, tried to avoid sharp corners that can introduce hot spots, and then we can also texture the die, the surface of the tool, to help fill out the cavity. And this is some old data from 1972, which shows the effect of die roughness on casting quality. And so basically, as they roughen the die surface, they were able to get better quality. And this is especially important for large thin wall castings, where you can get better flow, better fill by texturing the die. So if we look at the shape of the casting, as I said earlier, there's lots of guidelines available from NADCA on how to modify casting design to make it better for die casting. We got the NADCA publication shown here, the E606, product design for die casting. We don't have time here to go into the details, but this shows some examples here on the optimum fillet design for improved flow and reducing porosity. But here, one of the things we might want to think about in terms of heat traps. So it's not just the impact of the casting shape has on die filling. We also need to control the heat flow within the casting and within the die. We need to avoid these heat traps. And what is a heat trap exactly? So at any corner of the casting, so if we look at this left-hand casting, any corner of the casting on an inside corner, we're going to get a thinner section of the die where there's more heat. There's heat coming in from different directions, so it's going to run hotter in this area. We're going to get a concentration of heat, and we get a heat trap in a die. And so this potentially can introduce porosity. And so we can not only get heat traps in the die, we can also get heat traps in the casting. We've got a thick section here where three faces are coming together. It's being fed by thinner walls, and so this thick area is going to take longer to remove the heat, and so it's going to solidify last, and so we have the potential for getting porosity in that area. So if we go from left to right, we're going in the wrong direction. We're adding more heat, plus we're getting thinner die sections. Obviously, this is something we can't always avoid, but we need to think about it up front. Maybe we need to try and get more cooling into the area to try and remove some of this additional heat. And then core pins too. Core pins can also create heat traps. Shown here is kind of a classic example where we're often adding cores. We want to try and remove metal and remove heat from a thick section of the casting with the goal of trying to reduce porosity. Well, in some cases it can backfire on us. For a small core pin shown here, the core pin is going to get very hot, and it can actually encourage porosity. So depending upon the depth of a hole, a core pin can either help in terms of minimizing porosity or actually hurt and cause more porosity. So with long, thin pins, such as the one shown here, so where the length of the pin is much more than the diameter of the pin, we might actually consider getting rid of the pin, or alternatively, we can use a die material with a higher thermal conductivity, such as anvaloy. The cost of the pin from anvaloy is going to be more than that from H13. So up front, it's going to be more expensive, but maybe it'll reduce cost in the long run by minimizing the generation of scrap casting. So let's look at this heat trap from core pins in a little bit more detail. And so what we're looking at here is the impact of the core pin size on the porosity production. And so we're looking at data here for zinc alloy number 3. And we've got 2-pin diameters, 8mm diameter pin and a 10mm diameter pin. And then what we're showing is the impact of pin length. And this is the data here in terms of the amount of heat extracted. And then this is the pin diameter in meters. And so 0.005 meters is 5 millimeters. This is 10 millimeters and then 15 millimeters. So basically, if I go to a 1-to-1 ratio, so we're talking about an 8mm pin, so we're talking about 8 to 10 here. So this is for regular H13 with a pin length of 8 to 10 millimeters. We're at 25% efficiency. So basically, we can only remove about 25% of the heat that's going into the pin from the liquid aluminum. If we use a higher thermal conductivity mold material, such as Molmax, this is the data shown here for the same diameter. Basically, we can remove more than twice as much heat. So now we're at about 65% efficiency. So we're much less likely to get shrinkage associated with the pin from the heat trap with the pin. So basically what we want is short pins with the largest diameter. And so the length of the pin and the die material is going to have a strong impact on the formation of porosity. So if we now talk about gating, the goal is to design so we can manage heat. So we want to gate into a section where we can get directional solidification. And we also want to prevent gating directly into a feature such as a core that's obviously going to cause potential problems with soldering and things like that. So in terms of design features, we want to limit slides near critical areas and also give us enough real estate so we can get the vents, overflows to allow better filling of critical areas. So if you're the casting designer or you're working with the casting designer, you want to look at the final design. What can I do to improve castability? What can I do to dramatically reduce the cost of making the casting in terms of having to throw parts away through scrap. We need to think about designing for impregnation. There are things that we need to do if we decide early on that we're going to impregnate. A little bit different than we were talking about before. Before we're talking about trying to avoid porosity. Now we're talking about making it easy to fill pores with the impregnation material. So certainly impregnation materials today are very flexible. Materials can go to very high temperatures, 430 degrees Fahrenheit. One of the biggest design issues is we need to avoid blind holes if we can. If we can use through holes, then it becomes much easier to fill the holes with the impregnation material. Also shot blasting. If you are shot blasting and casting before you're going to impregnate, then you need to only do minimal amount of shot blasting. One of the problems, if you heavily shot blast it, then the pores can get covered up with a thin skin. And then it becomes very difficult to get the impregnation material into the holes. As we said before, we're only filling holes, we're not improving mechanical properties, so it's not suitable for fixing cracks, only for filling pores in leak-tight components. If we're designing for castings, a general rule of thumb is that we only want to 100% impregnate when, say, more than 30% or so of the castings leak. If maybe only 10% of the castings leak, it might be more cost-effective to do 100% leak testing and then only impregnate those castings that are leaking. However, some of the guys that do the impregnation saying these days, often today it can be more cost-effective to just 100% impregnate. So maybe that's something to think about ahead of time again when you're designing for castings. We talked about alloy selection quite extensively in some of the previous webinars in terms of the length of the freezing range of the alloy is going to control the type and the size of porosity. So if we want to maximize ductility, maybe we want to use a longer freezing range alloy as it's going to produce smaller pores, while a narrow freezing range alloy is going to produce bigger pores, which potentially going to have a bigger impact on ductility. So alloy 413's got a pretty narrow freezing range, and so potentially can produce larger pores, while alloy 380 has got a much wider freezing range, and so it tends to distribute the porosity more. You're going to get about the same amount of porosity, but it's going to be better distributed and smaller pores. So if you're struggling with a pore critical area, maybe it might be worthwhile to consult with a metallurgist to help identify the alloys that will give you a better distribution of the porosity. Obviously, one of the reasons why we pick different alloys, the alloy and elements are going to change mechanical properties and also change the porosity tolerance. For example, iron. Iron's getting a lot of attention recently, and iron could have a big impact upon the ductility of the castings, and that's what's shown here in terms of the elongation as we increase the iron concentration. Something else worth thinking about is sometimes it might be necessary to narrow the chemical specification range for the alloy you're casting. Certainly this happens quite a lot for the high-volume automotive die casters. So the data shown here is the range of properties available with 380 just based on chemical changes, or changes in the chemical composition, but within the chemical specification itself. So what's shown here on the top is this is the low end of the range in terms of copper, silicon, iron, etc., and then the high end of the range. So basically copper can go from 2.9 to 3.9, silicon 7.3 to 9.5. And so what people did is they cast these alloys. This is towards the low end of the range, at the high end of the range, and they got tremendous difference in properties. So at the low end of the range, you tend to get lower strength but higher elongation, while at the high end of the range, you tend to get higher strength and lower elongation. So you can go from 6.5% elongation down to 2.6% elongation just by varying the alloy and elements from the top end to the bottom end of the chemical specification range, i.e. from having all the elements at the low end to all the elements at the high end. So again, this might be something to think about in terms of narrowing the chemical specification range. So what does this mean? So generally we want to lean towards thin wall castings with a uniform thin wall. We need to think about heat traps, both in the casting design as well as the core design. Short cores can help eliminate porosity, while long, slender cores can attract porosity. And then remember that small changes in alloy can create large changes in porosity and also in properties. So let's talk a little bit about tool design. Once we've designed and built the tool, then we've got to actually fit it on a real die casting machine. So we've got to control, these are the parameters we're showing here. So here's some data from the 1970s from a paper from 1972, and what we're looking at is the percentage fill of the shot sleeve, and then also different vent areas. So looking at vent area from 0.08 square inches, and then doubling it to 0.16 square inches. And what it shows is that large vents, i.e. the solid triangles and circles, large vents gives you less porosity, a higher quality rating, both internally and external quality. And as we discussed in the last webinar, the fullness of the shot sleeve, the percentage fill in the shot sleeve, higher percentage fill also reduces porosity. So for example, if I have a die and I put it on a larger machine, I'm likely to have a lower fill percentage in the sleeve and then potentially having more porosity in my casting. So that's something to think about when you're putting a die on a machine. Then obviously PQ squared, we need to optimize the die for the machine, and to do this obviously we use PQ squared. To make sure that the machine is capable of filling the die the way it was designed to be filled. And then we also want to think about the gate size and the location. And so we've got a simulation here, and what it's showing basically is that the thicker gate we're going to reduce porosity. So here's the in-gate thickness on this simulation. So the gate is obviously down here. We're filling from the bottom. So the gate was 1.6 millimeters thick, and then we increased it by 0.4 millimeters to 2.0. So the gate has now been increased to 2.0. And what we see is we get a slight reduction in porosity. Porosity goes from 1.72 to 1.55. And basically it's because we can feed longer. The thicker gate is going to stay liquid longer. It's going to take longer to solidify, and so we can push more metal into the mold for a longer time, and therefore that's going to help us minimize shrinkage porosity. One thing we need to think about is that we need to watch for runner thickness, make sure the runner doesn't solidify before the gate. If we keep increasing the gate thickness, again, eventually the gate is going to be thicker than the runner, and the runner will solidify before the gate. The other thing we have to look out for is in-gate porosity. As I make the gate thicker, we tend to move the heat trap and therefore the hot spot from inside the casting and move it to the gate, and so we can get porosity at the gate. And so the data shown here for a large powertrain component, they probably don't care about in-gate porosity unless it causes a problem with leaking, and this is the in-gate porosity we can kind of see here. But obviously if we're talking about a cosmetic component, then in-gate porosity is going to be a big concern. And so we need to keep that in mind when we're thinking about in-gate porosity. And then talking about runner size and location. Runners obviously have got to be large enough to provide the required flow. We want to avoid cavitation, we want to avoid air entrapment, and so we want to have a smooth transition from the runner to the gate. The runner needs to be balanced for the size of the gates. If the runner is too thin, then it's going to solidify before the gates, and then the runner is the one that's going to control the porosity formation. If the runner is too thick, then we're going to reduce casting yield, which means we need to melt more metal, and therefore we're increasing our costs. And so we also want to think about the aspect ratio of the runner, keeping in mind that the aspect ratio is going to control how the runner solidifies. So if we use this thinner runner, shown here on the left, then we're going to get premature solidification. Then we're going to get faster solidification across the thickness. So if we're concerned about porosity, we want to keep feeding the channel, keep the feeding channels open as long as possible. So maybe we want to stay away from this kind of runner design and maybe move to this kind of runner design where we've got closer to a 1-to-1 thickness to width ratio. This is obviously going to stay liquid longer, and therefore it's going to provide better filling. So let's move on and talk a little bit about venting and vacuum. Obviously, for all our dies, we need to make sure that the die has got adequate venting. The cavity is going to be filled with air before we put the metal in there, and if we don't push that air out of the cavity, it's going to be trapped in and it's going to appear as porosity in the casting. So generally, the air moves very quickly. We can get a shock wave. That's what's shown here. This is a shock wave when you exceed the speed of sound, and this can occur in die casting also. And generally, we don't want to do this. We don't want to exceed the sound barrier when we're venting metal out of the die. We do have to develop pressure to get the air out. That's what's shown here on the left, where we're looking at pressure in the cavity, and it's going to increase with small events. That's what the data is showing here, looking at different size of venting. And we don't really want to develop high pressure. We want the air to be able to escape easily out of the cavity so we don't trap it in the casting and produce porosity. There's a number of ways to calculate vent sizes, one of which is shown here, where the area of the vent is equal to the flow rate of the metal into the die in inches cubed per second divided by 8,000. And so 8,000 inches per second is basically about 70% of the speed of sound in the die cavity. Another way to calculate vent size is the vent area is about quarter of the area or more of the gate area. So for instance, if a gate area is 1 square inch, then we need at least a quarter square inch of vent. Or we can use vacuum. And certainly high vacuum is the best way to go in terms of minimizing air entrapment. And this can be used if we can't get the air out of the die fast enough. We can go to high vacuum. There's lots of turnkey systems out there in terms of the high Q process, in terms of Vacural. But as we talked about earlier, it's critical that these need to be designed into the tool. You basically can't patch these processes onto an existing tool. You need to go straight to the high vacuum process when you're designing the die. Here's a little bit more information about venting in terms about the vent size and its impact upon pressure in the cavity. This is from a NADCA paper again from 1990. And so what we're looking at here is the vent size in square inches. And what we're seeing is the vent size increases, then the pressure in the cavity decreases. And so therefore it's we're building less pressure, and therefore what we're showing is it's easier to get the air out of the cavity. And so again, it's really critical to make sure that we have adequate vent sizing. Vent location is obviously also important. we need to make sure the vents are in the correct location. On the left is looking when we're filling more with a looks like a semi-solid process, and we can see that the metal is filling the die basically from the left-hand side of the cavity to the right. And so the last part to fill is going to be over the right-hand side here, and that's where we want to place the vents. On the right here, we're looking more of a conventional die casting process where the metal is shooting across the cavity, hits the end, and then it's rebounding. If we place the vents here on the right-hand side, you can see here in the middle one, the vents are going to be closed. It's going to be blocked by the metal very early in the process, and all this air, therefore, has got nowhere to go. There's no vent, and therefore it's going to become trapped in the casting. So with this type of a casting, you really want to have the vents down here on the left-hand side of the casting, or maybe even better, maybe have vents both on the right and the left. Then moving on to die cooling lines. So if we finally have the gates, the runners, and the vents in the correct location and the correct size, now we need to think about controlling the thermal aspects of the die. And certainly this is pretty complex. NADCA has a 2-day class on controlling the thermal aspects of the die, and often this is not well understood within the industry. So we really need to spend quite a lot of time to make sure that we have the thermal aspects of the die correct. We want the tool engineered well to control the solidification process. Here's an example where we've changed from oil to water, and we were able to move the thermal lines closer to the die surface, and therefore able to reduce cycle time as well as reducing porosity. Here's another important aspect. Often casters will move cooling lines so far from the die surface, so far back from the die surface, they become less effective. They're more concerned about maybe cracking or early breaking of the tool, and so they want to keep their cooling lines well back from the surface. And this can be a problem, though, because it doesn't provide very good heat extraction. So the orange line shown here, this shows the ideal amount of heat that I can pull out the die with a 3/8 inch diameter water line, while the blue line shows what happens when I put the water line 1 inch back from the die face. So basically 1 inch back, you have little impact upon the heat transfer. You lose a tremendous amount of the heat transfer because you can't move the heat through the steel. So if I want to control die temperatures, I need to get the cooling lines as close as I can to the die surface. And in fact, there's been some NADCA research recently on the effect of moving die cooling lines closer to the die surface. So a final point, let's just talk a little bit about squeeze pins. And squeeze pins are used on castings where we have an isolated heavy section. If you have maybe a thin wall casting but you have an isolated heavy section a long way from the gate, then obviously you're not going to be able to feed solidification shrinkage in that heavy section from the gate, because the thin wall part of the casting is going to freeze off faster, and so potentially you can end up with a lot of solidification shrinkage porosity in the isolated heavy section. And so with squeeze pins, we can apply pressure to an isolated part of the casting, basically providing localized intensification. But one thing that's really important is that the timing is critical, the timing of the application of the pressure of the squeeze pin. If you do it too early, then you're just pushing on the liquid metal and you're having no impact. If you do it too late, the metal's already solidified and you're just pushing on solid metal, and again you have no impact. So timing is very important in terms of the application of the squeeze pressure. And here's a paper from '08 kind of talking about the configuration. So basically you've got a squeeze pin cylinder where we provide pushing on the metal, and it's activated by a separate cylinder shown here. Okay, so basically what does this mean? What we're saying is that tooling design has a huge impact on the effect of porosity. And so we need to think about that when we're designing our castings, and we need to use the engineering tools that are available to us to design the die casting die and design it well.